Hi, welcome to session 6. We're going to be looking at the gradient and intercept and how it helps us interpret real life graphs. So graphs that have some real context to them. Before we do that, we are doing our recap. I'll scroll through slowly in case you're using the screen. It's obviously getting quite big now, so it could be for you that you've got to a stage where your recap is a session in itself, and then you come back and you do the new learning at a separate time. You absolutely have to learn at the right pace for you. Please don't treat this as a test. If you get stuck, go and look things up and help yourself, okay? Okay, let's do these questions. Okay, so you can see that I've highlighted B. It's this little bit here can often cause a little bit of confusion. Having the negative in front of the A, can really muddle some students. So I wanted to mention it just to be on the safe side in case that one did go wrong for you. Remember that that minus in front of the A is -1, so it does need to be pulled away, and it is a -1 that's kind of acting in the problem. However, that said, I really like thinking about, I'll just rub that out, I really like doing it in a slightly different way. And if you kind of see this and think, oh, I like that, then it might be something that you want to play around with. So that was our question. I can't promise you I do this every time, but my brain does work like this. I see that -A and I know it's going to be a problem. So I just think, all right, if I pick the -A up and I move that, even though that's the thing I'm trying to get on its own, but if I move that, it's got to land positive. So F is already there. My A is going to land as +A. And I end up with this. Now, obviously, A is not on its own. In fact, all I've done is move it to be with something else, but it's made it positive, which means when I now move the F, which is positive, it will land as take. And I'm not having to think about dividing through by the -1. You know, A is positive, is now on its own, and it equals 5D minus F. So it's an alternative way. It's not a wrong way of trying to deal with that negative if it's just kind of messing you up a little bit. Okay. So we've got our simultaneous equations. Here, I'm just trying to show you the F shape. Okay. That is angles on a straight line, and then corresponding angles helped me solve it. It's not the only way to do it. You know what it's like with angles questions. There are different routes around it, but that was the way I chose to do it. And last but not least, you have those. And for question 6, just remember y has to be completely on its own. And obviously, as you bring that divide by -2 round, it's going to act both on the -5 here and the -10 there. The two negatives turning things positive. Okay, so quite a big recap of learning, isn't it? And a lot of high-end knowledge going into it. So hopefully that has gone well for you. Real life graphs. This is a graph. It's a distance time graph, which means it is talking about a journey that has been measured, and it's been measured in minutes and in distance, and they're plotted together to create this graph. So at this point here, I haven't gone anywhere. I'm literally just getting ready to close the front door. As soon as I slam that front door, I'm off on my journey. I've like hit the stopwatch and I'm timing it. And you can see from the first part of the journey that I've traveled a distance of 12. It's taken me 60 minutes. And here, this is telling me that I'm not actually going any, my distance isn't going any further. It's not changing. It's staying exactly there.
So time is ticking on, it always does. So imagine if I'd cycled into town. Here it is. I've met a friend. We're having a nice cup of tea and we're sat literally not moving, just chatting. And then I travel home again. So I want you to work out the gradient of each line and then hit play when you're ready. So L1 is equal to 12 over 60. Now, you wouldn't tend, when you're interpreting, to go into decimals. I really need to see the numbers that are rising and running, okay? It's really, really important, because when I put the units in with it, it tells me a lot more about the journey itself. At the moment, they just look like a couple of numbers. It just looks like a fraction. But if I actually put that the 12 is 12 kilometers and the 60 is 60 minutes, I can now confidently say, I've traveled 12 kilometers in 60 minutes, or I've traveled 12 kilometers in an hour. And when you do it like that, you, one, can see if there's any additional connections you can make, but you can make a firm statement about the gradient. It's not just the gradient's 12 over 60. Don't really know what that means. It's just 12 over 60. Here it is, I will travel 12 kilometers in 60 minutes. So it has context. Or I will travel 12 kilometers in every hour. Hoping that you've noticed that this unit, this kilometers per hour, is also a measure of speed. So my gradient isn't just a line with a, steepness attached to it. It's actually giving me the speed that I'm traveling at. So when I travel this distance in a certain time, I create the speed. And the three are really absolutely connected. So you should know, hopefully, that you've got your distance, speed, time. Speed is found by doing distance divided by time. That is exactly what we just did. Distance, 12 kilometers over time, 60 minutes. Gradient. So gradient actually gives us the rate of change that's happening. And the rate of change is 12 over 60. So there's a lot of information, but the main point is they're not just numbers. They actually really do mean something, okay? Now, I'm hoping that you put that line 2 has a gradient of 0. And then line 3 is just, again, we've got the same rise because we're traveling the same distance. We are doing it in less time, which means you could interpret this as a part of the journey that's the fastest. It's taking me less time to travel that distance, so I must be traveling faster. And if we worked those so that they had the same denominators, we would actually see that. But we are moving on because I really want to see a couple more graphs before we go on and practice. So this is a conversion graph. It's taking euros into pounds or pounds into euros, depending on what you're being asked. And these are quite common, and we can be asked really quite simple, basic questions. So if I was asked, for example, how many pounds would I get if I had 40 euros? Let's say that was my question. Oops, you can't even see it. Let's bring that down a little bit. There we go, bring it across. So how many pounds am I getting if I've got 40 euros? And we have learned to read the graph, find 40, come along and hit the line, come down, and your answer is 30. So it's 30 pounds. So absolutely correct. But if you notice, those markings are also a run and a rise. All right. Obviously, if I was doing a run and a rise in the way that I've been taught, then I would have come across and run first, run for 30, and then I rise for 40. And I end up with a gradient that actually has some meaning, okay? What I'm going to do is I'm going to divide by 30. The reason that I'm going to divide by 30 is because I want, wherever possible, to be able to talk about it in its simplest terms. So if I do this, I will end up with, let's just do it quickly in my calculator. I will end up with 1.3 recurring, and obviously I'll have 1 on the bottom. So when I do that, that doesn't give me the nicest of numbers. It is telling me, okay, because my pounds are on the bottom and my euros are on the top, it's telling me that for every pound, I get 1.33 euros. Now that is a rounded version, so it may not be sensible to go to the 1. It may be better to just divide through by the 10 and say that for every £3, I get 4 euros. There's nothing really wrong in saying for every £30, I get 40 euros, because it's still true, isn't it? But they generally like it simplified down and then interpreted. So I always go to 1. 9 times out of 10, you end up with a number that's pretty sensible and you can make a comment about what you're looking at. But sometimes it doesn't quite work out. So I've obviously demonstrated where that's happened. You know, 1.3 recurring is 1.33333. And I've had to round, which means I lose some accuracy. And I don't want to lose accuracy, so I'll go with another option that would make it make more sense. And I certainly wouldn't scribble any of that out. If I did that on my exam paper, that's part of my workings out. It kind of justifies why I went to £3 giving every 4, because I'm trying to demonstrate that I want to be as accurate as possible. So that is a way of using the gradient on a graph like that. You're kind of using it without even realizing it. Okay, I think one of the most important things is to realize that it's not really about the graph as it is about the story. The graph just gives me some numbers that I can get, and then I can start using those numbers to create an interpretation. But the context, the narrative of the story is actually more important. And I've tried to show that by showing that this one single graph could fit with all of these stories. So I could be talking about a taxi firm that has a number of minutes that you're in their taxi for. I could have the cost of hiring a hall based on the number of minutes that you book. I could say that this graph is about how the water in a paddling pool is warming up in minutes over the course of a hot summer's day. The story is what will help you interpret the gradient. The gradient is just a set of numbers. So really, it's not so much about the graph as it is about the story. So let me show you what I mean. If the graph was showing the cost of a taxi firm, okay, the first thing that I need to notice is it starts at 20. It's not starting at 0, it's starting at 20. So that is suggesting that they're going to charge me £20 just for getting in the car. And then they're going to charge me by the minute. So the y-intercept actually does give a piece of information about the story as well. So you've really got to think in context. So I haven't traveled any minutes. Yeah, I haven't moved along this line at all yet. I have literally I'm just at 0. So that's how I know that there is some sort of standing charge. And so they're going to charge £20 as a flat rate. Okay. And then I look at the gradient. So like I say, I really am a fan of extending all the way along because it's easy to see. So I've got 500 as my run. My rise is positive. It's going up. And it is going up 15. Would we agree? No, we wouldn't. let's double check this. So it's going 20, 30. Yeah, I would say 15. Okay. Now, I've said, if you can get it down so that one's on the denominator, you can often talk a little bit easier about what is happening. So I'm going to divide through by 500. Okay. And that is going to give me 0.03 on the top and 1 on the bottom. So what this taxi firm is doing is it's charging me £20 flat rate, and then it's going to charge me 3p for every minute that I spend in his taxi. Okay, so that's the interpretation of that story. The cost of hiring the hall is virtually the same because it's obviously the same gradient. It means that there is a flat rate of £20, and then I'm going to be charged 3p for every minute I stay in the hall. The water is slightly different because it's not about money anymore. It is about how much paddling pool is warming. So here I would say my y-intercept of 20, I would say, okay, the temperature of the paddling pool before the sun came out is 20 degrees. And then it's warming at a rate of 0.03 degrees every minute. Okay, you could go into hours. I think if the story's in minutes, it's easier generally to stay in minutes. If the story's in hours, it can be easiest to stay in hours. You've got the option of changing between. And again, it really depends on the graph and the story, and everyone is different. So we're trying to cover lots of ideas with the couple of graphs or so that we're going to do. And then it's just a case of just diving on in there, okay? So the narrative, the story is going to help you put the words together, because these really are questions that they expect to have sentences as answers. You can't just work out the gradient. Let's say you worked that out and you left that on. You might get a mark, but you're not going to get full marks because you're not explaining it. You're not giving a reason to these numbers. They're just numbers. Okay. All right, let's take a look at this one. So this graph shows the volume of water in a swimming pool as it drains for a deep clean. Okay, so I'll bring that down so you can actually see it. So it drains for a deep clean. So what I want you to do for this one is think about the context of the story, press pause, and then just come up with how you would describe what is happening. What is the graph? The story is telling us the story, the narrative. The graph is telling us the numbers that the story is creating. We've got to put the two together and interpret what's actually happening here. So hit pause and press play when you are ready. Okay, so let's interpret the start of the line, which is here. So that is telling me that there is 210 centimeters cubed before the plug is pulled. Okay, so that's what that's telling me. So let's write that down. So pool has 210 centimeters cubed of volume before plug is pulled. Your sentence could very well be different to mine, but if it's the same gist, then it's fine. We're all going to write a slightly different sentence, okay? Then I've got to look at the gradient so I can talk about the rate that this is happening at, okay? Because gradient gives us a rate of change. So my run is all the way across. So I have a run of 140. And then I'm going down. So I know that this is going to be negative. And it's 210 on the top. Now, the negative is there to tell me that it's a negative gradient. It doesn't necessarily need to be part of the actual story that we're telling. So I can cancel that down. I can also see that 7 goes into both these numbers. So I've got 3 over 2. If I divide by 2, I can get myself to 1.5 over 1. So think about those numbers. The 210, the rise, is my centimeters cubed, and my run is my minutes. And honestly, getting those units in place next to those numbers makes it so much easier to put that story together. So now what I can say is that we could say that the pool is draining, whoops, can't spell. The pool is draining at a rate of 1.5 centimeters cubed every minute. And again, your wording may very well be different to mine. You may have stayed with the numbers 3 and 2 and talked about how 3 centimeters cubed was going out of the pool every 2 minutes. And that's still correct. You have interpreted that gradient in context to the story. And that's really what they're looking for you to do. Okay, so that's it in a nutshell. It will feel a little different as you're learning it because every story is different and you kind of have to get your head around it. But one of the easiest things to help you is that bit there. That immediately makes sense of the numbers. So bring it in and sit it right next to those numbers, and hopefully that will be a good way of helping, because I know it's hard.
Right, so what we're going to do now are some practice questions. Let's get the first set up so you can see them properly. Hopefully you have been able to print the page from the workbook, or you have the workbook itself, because it is going to make this easier. There's just the 4, and then I will see you next session. So all the best with this. Well done today. And I'll just scroll through now.